Okay, so we are going to pick up today with, we're continuing to talk about conservation biology, and we're going to pick up with landscape and regional conservation. So last lecture we talked about saving individual species. Now we're going to talk about saving areas where there are multiple endangered species. So we've had a shift in the last few years as far as conservation efforts are concerned from saving just one individual, or do we save an entire ecosystem where there are many individuals who might be benefited from kind of attention in that regard. So I want to start by talking about edges of landscapes, because if we're going to be saving ecosystems, we have to kind of figure out, well, where do they start, where do they end, and what are the features of the landscape that we're actually trying to preserve. And what we've learned is that the edges of landscapes have their own very specific set of physical conditions that are different from the landscape on either side of it. So for example here, this is an aquatic ecosystem, and this is a dirt ecosystem. I'm sure there's a fancier name for it. But the edge here has some properties of both of these. Makes it unique. Same thing here, forest ecosystem, dirt ecosystem. The edges have different features than the ones than the features of the ecosystem on either side. And so it turns out that there are some organisms that actually thrive in these edge communities, and they do that because they gain resources from both adjacent areas. So you might be, we call them edge-adapted species. These are the organisms that live on those edges, but then get stuff from both ends, okay? But then there are other organisms that actually stay away from edges as much as possible. So why I bring all this up is because when humans alter ecosystems, we add edges. We build a road, and that's an edge. Right? Or we add a power line, and we have to cut down a whole bunch of trees in order to add a power line. That's an edge. So when we add edges, road construction, redirecting rivers, whatever it might be, oftentimes they'll have reduced biodiversity and increase edge-adapted individual populations. For example, there's a kind of bird named the cowbird. The cowbird, it turns out, is a jerk. Let me tell you why he's a jerk. He is an edge-adapted species. He forages, so he gets his food from open space, but he lays his eggs in nests of other birds who live in the forest. Here's what this particular one does. Pearl, because it's the girl laying the eggs, hangs out on the edge of the forest and waits for a songbird, another bird, to build a nest and lay an egg in it. And then when the songbird is out foraging for themselves, along comes the cowbird and was like, nope, literally kicks out the egg, down to the ground splat, lays its own egg in the nest, and then flies away. The songbird isn't a sharp bird, not real bright. Songbird comes back from foraging, doesn't recognize the switch that has occurred. So then the songbird incubates the cowbird's egg, and then sometimes songbirds will have clutches of more than one egg. That's like having 2 eggs or 3 eggs at a time. We call that a clutch. Might lay some other eggs, doesn't realize that the first one's not like the others, right? The cowbird egg has a faster developmental cycle. So which one hatches first? The cowbird. So which one grows faster? The cowbird. Which one can beat up all the little ones? The cowbird. So the cowbird baby hatches. The songbird feeds it because it thinks it's its own. The baby songbirds hatch, and the cowbird is literally the big bully of the nest and kicks them out, or they starve to death. Oh, it's appalling, isn't it? That's appalling. Totally a jerk. So that cowbird is an edge-adapted species. It has to eat in the plains, kind of in the open space, but he has to lay his eggs in the forest. So as humans add edges, they're allowing more environment for that cowbird to be successful. What we've found is that many, many, many species of songbird in North America are now endangered because of adding edges. Not even necessarily reduction of habitat as far as acreage is concerned, but simply adding edges and allowing another species more area to compete is becoming very challenging for many species of bird. So it's just an example. In fragmented habitat, sometimes we add movement corridors, okay? And so these can be really useful for conserving biodiversity. For example, this is a fragmented habitat where we have trees here and here and here, but getting across this is like a desert, right? They can't get over there. And so we can add movement corridors to help organisms get across an edge, in this case. We've just started building some of these in Colorado. They built one bridge and one tunnel up in the mountains. And they just opened, or they just finished construction, most of construction in the spring. They still have more fences and stuff to build. There were a lot of people who thought these were not going to work in Colorado, but literally, as soon as CDOT opened it, or I guess Division of Wildlife, they could see that right away the deer and the elk were using these tunnels immediately. So the reason they built one bridge and one tunnel was because they didn't know if one would be better than the other. And so then they were going to collect some data to see which one was better than the other one. And then moving forward, they would just focus their attention on that particular type. And what they're finding is that the organisms seem to be using them both fairly equitably, which is pretty cool. But so if you're driving up in the mountains, there's a very real possibility you would see these wildlife bridges. Why are they useful? Well, they're useful because it promotes dispersal of organisms, reduces inbreeding. And here's a big one that even if you don't like animals, you probably like your car. It reduces the number of animals killed crossing highways. And if you've ever known somebody who's hit a deer with their car, that will change your day. In a lot of ways, it will change your day. You can get killed hitting deer. And so adding these kinds of things is good for both humans and animals. So conservation biologists work with governments to establish areas to slow biodiversity loss. And that right now, about 7% of the world's land is set aside somehow to slow the loss of biodiversity. We call those biodiversity hotspots, the places where we should focus our energy. Those hotspots tend to be a very small area where numerous species are found nowhere else in the world, and a large number of those species are either endangered or threatened. Nearly 30% of all bird species can be found in hotspots that make up only 2% of Earth's land area. So when we start thinking about conservation biology from the context of saving an ecosystem rather than saving an individual, we would want to focus our attention on these hotspots. Here's a map of hotspots. The blue triangles are indicating marine hotspots, and then the red is indicating our land or our terrestrial hotspots. Last class we talked a little bit about Southeast Asian region and just how much diversity we're finding is there, but nobody's really ever looked for it. That whole area is considered a hotspot because there's so many species and so many of them are endangered. Hotspots are good choices for nature reserves or preserves in order to help save species, but identifying a hotspot is not an easy thing. A hotspot for one group of organisms may not be for another group of organisms, and identifying hotspots tends to be biased towards saving vertebrates and plants. Turns out we don't really care much about saving bugs. But you have to have the bugs because they're toward the bottom of your ecosystem, right? And so we have to be careful about putting too much emphasis on our food webs and the organisms that are on the top of the food webs without supporting them sufficiently throughout the bottom of the food web also. The other trick is that identifying and preserving only hotspots puts a lot of emphasis on a very small fraction of the Earth's surface. When we do that, if we were to only save 2% like we had on the last slide, but to pollute like crazy on the other 98%, well, that 2% is not going to last real long because it's one globe and all of these chemicals are cycling regardless. We're going to spend just a few slides here talking about human actions and how Earth is changing as a result. So, environmental changes that are caused by humans create challenges for conservation biologists. For example, what if the location of a vulnerable species found today is not needed for preservation in the future? So let me give you an example of this. What's going to happen to Florida in the next 150 years? Well, it's not going to sink. The water's going to rise, and so it'll be under water. Are we sure? Not 100% sure, but it seems likely. We can watch what's happening like in Venice. Venice is going underwater, right? And we can see that what's happening in the Everglades is that the water is very slowly creeping up. So here it is. Is it a hot spot? Yep, that's the Everglades. But 150 years from now, if it's under another 18 inches of water, will it be a hot spot? Maybe, maybe not, right? We have no idea. So do we put a lot of effort and energy into saving that hot spot if 150 years ago it may, or 150 years from now, that might not have been a good use of time and money? So we come to this question. This is an issue for conservation biologists. What do? We have limited funds, obviously, and limited people to do this kind of work. How do we prioritize our time, and what sorts of things do we take into account? Because of global warming, habitats on Earth are changing so quickly that the locations of preserves today may be unsuitable for those same species 100 years from now. And that's just because of how the environment is changing so very quickly. Okay? That organisms have to move or die. So we're going to look at 3 types of environmental change that threaten biodiversity: nutrient enrichment, toxin accumulation, and climate change. Human activity, we talked about this when I talked about my banana a few classes ago, and I said my banana came from Peru. I ate it for breakfast. The nutrients in that banana came from the dirt in Peru, and the nutrients in that banana are going to be deposited in the watersheds of Colorado. So we're moving these nutrients around the globe simply because we have a global economy where food is grown in one place and transported to another location. So this moving of nutrients, if you're a farmer, is dealt with by applying fertilizers. Well, a problem arises when farmers apply, and it's not just farmers, but it's also like golf courses and anybody who uses fertilizers, homeowners. The nutrients are added to the soil, but they don't all get absorbed. Some of them are included in runoff. So then we water, and then the water picks up some of those nutrients and carries it into the watershed. What that's called is exceeding, the nutrient level exceeded the critical load. The plants absorbed as much as they want, and the rest got carried away. Well, the added nutrient is how we have the eutrophication issue that we talked about with the water systems several lectures ago. The fertilizer gets into the groundwater, runs into the fresh water, and into the marine ecosystem, contaminating ecosystems and killing the fish. So here's a concrete example of this. The Mississippi River carries nitrogen pollution to the Gulf of Mexico. So the Mississippi River is the one that runs right down the center of our country, top to bottom, straight through the farmlands of America. Well, that's a prime example of a place where the nutrients in the dirt are going into the plants are being cut down and shipped to other places. So the farmers are adding the nutrients back in. Well, when we exceed that critical load, they water their fields, the water carries away the extra nitrogen. Where does the water end up getting? Into the Mississippi River. The Mississippi River flows all the way down the middle of our country, and it exits down here near New Orleans. So what ends up happening? A nitrogen influx into this part of our, the Gulf of Mexico, causes a phytoplankton bloom each summer. The trick is, just like in our freshwater ecosystems, when those phytoplankton die, their decomposition ultimately is going to lead to eutrophication. Well, what gets to live in eutrophic waters? Nothing. So, fish and other marine mammals disappear from some of the most economically important waters in the United States. Have you guys seen Forrest Gump? That movie? Maybe, maybe not. Bubblegum Shrimp Company, right? Where are they fishing for shrimp? Okay, true story? Yeah, most of the shrimp that we eat are coming from the waters down here off the Gulf of Mexico. So when we have these eutrophic waters, there's no shrimp here. That changes things for these people, right? As a practical example, again, city of Houston is like here. My parents live about here. My dad's a fisherman. So he has a flat-bottom bay boat, that's what he calls it. And he'll straight up tell me, he's like, in the fall, early winter, no sense in going fishing. There's nothing there. It's all gone. And I showed him this. I was like, well, you want to know why it's all gone? I'll tell you why it's all gone. This is what happens when your daughter's a biologist. It's like, I just don't get it. And I'm like, well, let me tell you. But late winter, spring, early summer, all of this has been carried away by the tides and the movement of water, the water currents. All of this gets carried away, mixed into the ocean ecosystem, and life comes back. But this is a cycle. It's an annual cycle that is caused by what's happening all the way up North America. All of those waters that feed into the Mississippi River are what's causing this massive bloom. So conservation ecologists are working to restore the wetlands, but there's only so much conservation ecologists can do, because what we have to start doing is not dumping so much nitrogen in the first place. Okay? It's easier to prevent the cause. Human activities also release a ton of toxic chemicals, many of which are synthetic, into the environment and don't understand what the consequences are. Synthetic means fake, right? Well, guess what? You can't metabolize fake chemicals, okay? And so as a result, they build up in your tissues, mostly in fat. So the toxins become more concentrated in successive trophic levels of a food web. Why? Because you can't metabolize them and poop them out. So if the toxins at the bottom of the food web are in very small quantities, when the fish eat them, that's all well and good, but the fish can't metabolize this, and because they have to eat so many, they build up. Those toxins build up in the fat of these fish. Well, then these fish eat these fish, and the same thing happens. Now we have even more parts per million, that's ppm, parts per million, a greater concentration of the toxins in the fish, and as we climb up the food web, or the food chain, the concentration is higher up here than it is down here, because down here, you can't just metabolize it and poop it back out. It gets stuck in your body tissues, and it stays there forever until you die. So what we end up with are top-level carnivores being severely affected by toxic compounds in the environment. A great example of this is DDT. DDT was used to control populations of mosquitoes after World War II. We thought it was the miracle chemical. It was solving all kinds of problems. Well, scientists realized later that DDT did not get metabolized, and it persisted in the environment, transported by water huge distances from where it was applied. Scientists started seeing huge declines in the populations of top food web water birds, pelicans, ospreys, eagles, for example. They tried to figure out what was going on. Well, it turned out the accumulation of DDT in the tissues of these birds prevented the female birds from depositing calcium in the eggshells. That's what makes an egg hard. So what do birds have to do? They have to sit on their eggs to keep them warm. So sad. The eggs were so brittle that when the mama or the papa bird would sit on the eggs in order to warm them, the weight of their body would crack the egg and they would literally kill their own babies. This did not take long to see catastrophic declines in birds' reproduction rates, okay? Because there were almost no babies because they were all being crushed. Those are crushed eggs. And so getting DDT out of the system took a very long time and took a very long time for the populations to rebound. DDT is still used, not domestically, but it is used to control mosquitoes that spread through countries in the tropics, especially malaria-stricken countries where mosquitoes can kill people with the diseases that they carry. DDT was used again very recently because of the Zika virus, right? We weren't really sure what was going on with that, but we knew that mosquitoes were part of the problem. DDT again was used. So there are definitely trade-offs between saving human lives and saving species, right? And we don't always have an easy answer to that question. Another way we get toxins into the environment is through pharmaceuticals. OTCs, over-the-counter and prescription drug use has risen dramatically in recent years, and much of it ends up in the water supply, so that low levels of pharmaceuticals are literally in all of the streams and rivers that we have here in North America. This isn't just a human thing, though. The use of drugs, specifically antibiotics, and hormones in farming, they use them to resist disease and increase output. All of that stuff is eventually washed into the watershed. Case study was done with a certain type of estrogen used in birth control. Birth control, or the pill, is something that women who are on it have to take every single day. Why? Because you pee it out every single day. Well, if you pee it out every single day, where's it going? It's going into the watershed. So now, all of the things that live in the water are also on birth control. Right? That's the end result of that. So there was a case study with this particular kind of estrogen, this hormone. Minnows that were exposed to the estrogens as eggs all developed into females. But that's not going to work out, because now we have no boys, and if you have no boys, you have no baby fish. And in 7 years, that species became locally extinct. 7 years. This was done at very low concentrations that were consistent with what's found in some waters in the world. So we know that stuff gets into our water and does not get back out, okay? And then our ecosystems are impacted by this. Human activities also release a lot of gas waste. Here at CO2, methane is another example of this. We once thought that the atmosphere could absorb all the gas that we could put into it. That's definitely not the case. Scientists estimate that the average CO2 concentration in the atmosphere before 1850, the Industrial Revolution time period, was about 274 parts per million. Today we're actually a little higher than 400 parts per million. That increase concerns scientists because of the link to increased global temperature. So this is our CO2 concentrations and our temperatures, and the massive up and down has to do with seasons, winter versus summer. Okay, that's what that has to do with. And this is very tricky because scientists see this as correlative, like there's this correlation, but we cannot prove a causal link on a global scale. Because how do we do an experiment on the globe? So this is very similar to the science, remember the Miller and Urey experiment where we tried to pretend like we had the atmosphere, right, and we sent it through those cycles? That's the kind of experiment scientists do on this, to try to understand how the atmosphere changes and what that's doing. But there are people who don't believe that that's an accurate reflection of what's actually happening on our globe, because we can't do an experiment on the entire planet, right? It's not possible. So why are the two linked? Well, even though CO2 is transparent, we don't see it, it intercepts and absorbs a lot of infrared radiation. Some of that is re-reflected as heat back to the Earth. We call this the greenhouse effect. We actually like the greenhouse effect because without it, the surface of the Earth would be about 0 degrees Fahrenheit. So the greenhouse effect isn't a bad thing, okay? The ecosystems at greatest risk are those at the poles and the coasts that are going to be underwater as the polar ice caps melt. So as our temperature goes up, the ice caps melts, more water is in the oceans, and then that causes sea level to rise and stuff goes underwater. However, those of us in Colorado that are pretty far removed from all of the coastlines are not immune, because this is causing, global warming is causing more extreme weather. So more fires, more drought, more blizzards, these kinds of things. So we have more swings in our weather as opposed to having more consistent weather patterns like we've experienced in the past. So while we can't reverse global warming, we can slow it down by using energy more efficiently and replacing fossil fuels with solar, wind, and power. Very interestingly, just in the last couple of weeks, Xcel Energy came out and said we'd finally tipped the scales. It is now more financially responsible for them to build a solar farm or a wind farm than it is for them to build a coal burning plant. And that has just happened. We finally switched it. The technology has gotten cheap enough that using these renewable resources are actually cheaper in the long run than building a coal-fired plant. This is really good news, because the reality is a lot of companies are going to act in the bottom line's best interest without regard for the planet. And so as we can get to this point of it actually not only being better for the planet, but also better for their financial bottom line, that's when we're going to start to see more and more renewable resources being used globally. So that's actually really good news. Everything we talk about doesn't have to be said. Human population is no longer growing exponentially, but it is still increasing rapidly. You may have heard this, human population growth is exponential. It's not. Because remember, exponential means we are growing at Rmax. Remember, we defined that. We are not growing at Rmax, and that's good news, but we are still increasing significantly. This has got a couple problems. We just can't keep growing forever. We will run out of space. The globe has a carrying capacity. Our planet has a carrying capacity for humans. And so the question is, where is that carrying capacity and how close are we to it? We grew exponentially from about the 1650s to the 1900s. But what happened here? You guys know? Not a war.
The Black Plague.
Bubonic plague, yeah. There was the plague. Okay, here we are. See how here in the 1960s is when we stopped growing exponentially. We're still growing a lot, but it's not exponential anymore. Okay. Currently, the global population is between 7 and 8 billion. We're increasing at about 78 million a year. The growth rates of industrialized nations are much slower than the less industrialized nations. Most industrialized nations, populations tend to be near equilibrium, near zero population growth. Replacement is the same as death. And so there are some countries that actually have negative growth. Canada, Germany, Japan, and the UK are examples of countries that actually have negative growth. But the other side of that is we are still growing, and that growth tends to be in less industrialized nations, which are growing at about 1.1% per year. 80% of the world's people live in countries that are less developed. So how many people can the Earth support? Somewhere probably between 10 and 15 billion, but that's a huge gap. And considering right now we're at about 8 billion, how close are we? Maybe close, maybe not, who's to know? Food is likely going to be the limiting resource, mostly because of transportation. Right? We can grow it, but we can't get it to where people need to get it. And so when we look at this question of Earth's population, we can look at it more comprehensively and call it the ecological footprint of each person. And that term summarizes the amount of land and water required by each person to produce all the resource that you consume and to absorb all of the waste that that person generates. All things being equal, with our current population, each person can have 2 hectares of Earth for their footprint. In the United States, a typical person is 10 hectares, so we're using 5 times more on average than we should. The U.S. also tops the range for energy use, which directly correlates to CO2 produced per capita. So we are bright red. So this is just saying per capita, per person, how much energy do we use? And the answer is more than any other place on the planet. Okay, we're the darkest red of any of them. That's us. Oh, so sad. Right? So the goal is for us to use less. All right, sustainable development is my last little term. We are not going to stop building. We're not going to stop building malls, building houses, building schools. That's not going to end. So that is called development. But the new push for conservation biologists is to develop sustainably. It's possible to have economic development that meets the needs of people without limiting the ability of future generations to meet their needs. So we have to find the balance between building and the ecosystem, doing it in a responsible way. And so in order to do that, we have to connect these concepts of ecology with the social sciences, economics, the humanities, in order to make sure everybody gets what they want, but that we're not damaging things for future generations at the same time. Done.